Hi, I'm Shahram Rasoolzadeh and I'm going to present our paper entitled Computing Expected Differential Probability of Differentials and Expected Linear Potential of Nonlinear Hulls in Substitution Permutation Block Ciphers. It's a joint work with Moriai Eichlseder and Gregor Leander, and it is accepted to Indocrypt 2020, which is going to be held virtually in India on 13th to 16th December. Differential and linear cryptanalysis are two powerful statistical attacks on symmetric cryptography. Differential cryptanalysis was first introduced by Biham and Shamir in 1990 to analyze security of the DES block cipher, which this attack was based on the probability of differential characteristics. And the linear cryptanalysis was introduced by Matsui in 1993 to again analyze the security of DES block cipher, and this attack was based on the linear correlation of linear characteristics. While these two attacks both were originally evaluated based on the differential or linear characteristics, it was soon observed that the relevant metric to analyze against these attacks are rather the probability of a differential or correlation of a linear hull. Moreover, Knudsen later introduced truncated differential, which is a generalization of differential attack, and also Kaliski and Rapshaw introduced the multiple and multidimensional linear cryptanalysis. Both of these generalizations consider collection of many differentials or linear mass to make the attack more efficient. To analyze a cipher's security against these two attacks, evaluating or at least approximating the probability of differentials or correlation of linear approximations is an important step, but usually it is not easy to do. In this paper, we worked on evaluating probability of differentials or truncated differentials and also potential of linear hulls and multidimensional linear hulls. But in this talk, I'm going to only talk about the probability of differentials, and interested people can check the paper. First, I start with explaining the general structure for substitution permutation block ciphers, or shortly SPN block ciphers. SPN block cipher is a round iterated block cipher, and each round includes 3 round operations. The first one is the substitution layer shown by S, which is a nonlinear layer, and it applies m-parallel bijective S-bit S-boxes to each word of the state. The second round is a permutation. That's a linear layer, and it is a multiplication of an n times n bijective binary matrix to the whole state. The third operation is the key addition that XORs the n-bit round key ki to the whole of the state. We showed one complete round by R, and also by R star we show the keyless round operations, that is a substitution and then a linear layer. In differential cryptanalysis, the attacker wants to find non-uniformity in the occurrence of plaintext differences alpha and the corresponding ciphertext differences beta. For an encryption with key k, the fixed key differential probability of a differential is defined as the given equation. Clearly, this value is dependent on the value of key. Since the attacker has no knowledge on the key value, he wants to find a differential with fixed key probability significantly high for almost all of the keys. Therefore, he wants to find a differential with a high expected differential probability. The expected differential probability of an encryption is defined as the second equation, which is the average of all fixed key differential probabilities for uniformly distributed key values. Since finding a useful differential is not easy to do, the attacker reduces the problem to find one or several differential characteristics, but with the same input difference alpha and output difference beta. In a differential characteristic, the difference in the input and in the output of each round is known, and here we show these values by alpha I values. For instance, here the input difference of first round is alpha 0 and difference value in the output of this round is alpha 1. And then again, the input difference in the second round is alpha 1 and the output difference is alpha 2. We denote such a differential characteristic by this notation. Follows that for a key alternating cipher, including SPN block ciphers, the probability of a differential is the sum of the probability for all containing characteristics whose plaintext and the ciphertext differences are the same as in the differential. Computing these probabilities is not an easy task to do, because for a given differential or differential characteristic, they need computation over all the message and the key spaces. In other meaning, the computation complexity is about 2 to the n plus kappa. Even for the smallest applied value of block and key sizes, this is an approachable complexity. One assumption that makes it easier to compute expected differential probability of differential characteristic is known as the independent round keys assumption. This assumption first was introduced by Leander and Murphy for the first time, and it was called Markov cipher assumption. In the independent round keys assumption, it is assumed that all the round keys are independent of each other. Leander and Murphy proved that under this assumption, expected differential probability of a differential characteristic is equal to multiplication of differential probabilities over each keyless round. This can be generalized to compute expected differential probability of a differential, that is sum of these multiplications over all the intermediate state values alpha 1 to alpha r minus 1. It is noteworthy to mention, in the case of an SPN block cipher, differential probability over one round is multiplication of differential probabilities over each of m S boxes. Therefore, expected differential probability of a differential characteristic is just reduced to be multiplication of differential probabilities over active S boxes in the characteristics. Computing expected differential probability of a differential characteristic under this assumption is very easy. We just need to compute the differential distribution of the S boxes beforehand, and then we only need to do lookup table for each of these active S boxes. But still, computing expected differential probability of a differential even under this assumption is not easy, because we need to sum over all the intermediate state values alpha 1 to alpha r minus 1, and this increases the complexity of computing. About the truncated differential analysis, as I said before, it is an extension of differential cryptanalysis, where the ciphertext difference can be chosen from the set U, and also the ciphertext difference can be chosen from the set V. Assuming that all the differences in the set U happens uniformly, expected differential probability of this truncated differential is defined as this given equation, where it is average over all input differences and the sum is over all the differentials that the input difference is chosen from U and output difference is chosen from set V. Note that in classical truncated differential, only differences in some bits of the plaintext and the ciphertext are determined, while in the other bits, the difference can be any values. In this case, U and V sets are special kind of linear subspaces excluding the zero value, but in our work, we use this general definition of the truncated differential. One way to make the expected differential probability computation easier is partitioning the underlying characteristics by their activity pattern. We define the truncated differential characteristics, that is, for a given activity pattern shown by a vector of delta i's. This truncated differential characteristic is the set of all differential characteristics following the given activity pattern, and we denote the expected differential probability of these truncated differential characteristics by this notation. Partitioning over the activity patterns and using the truncated differential characteristics helps us to compute expected differential probability of the truncated differentials, because for a given truncated differential, there are usually only few truncated differential characteristics with prominent expected differential probability to compute the expected differential probability of the truncated differential. Here in this figure we show a 5-round truncated differential characteristic for MIDORI block cipher that briefly saying each round of this block cipher includes S-box layer and then shuffle of cells which permutes the nibbles, and then mixed columns that a matrix manipulation is applied to each column. And then there is a round key, but for simplicity of the figure we remove this operation. In this truncated characteristic, in the first round there are 3 active S-boxes. And then in the second S-box layer there is 1, in the third there are 3, and so on. In the last round, again for simplicity of the figure, we remove the linear operations. To compute expected differential probability of this truncated characteristic, we need to look for differential transition probability over 25 active S-boxes and do the sum over 22 variables of A's, X's, and C's. Therefore, computation cost of this probability is 25 table lookups and the same number of arithmetic operations for each 15 to the 22 values of A's and X's and C's. That is, in general, about 2 to the 90 operations. There are several previous methods to compute expected differential probability of a truncated characteristic. That the first one is enumerating over all the differential characteristics, as I explained for the previous example. This is simple but inefficient. The second method is using matrices of transition probabilities, that for each input difference and each output difference of a round, you compute a matrix that each element shows the probability of a transition from corresponding input difference to the output difference. Then, by multiplying the matrices for the consecutive rounds, you can reach to the transition probability matrix of the whole encryption. This method only works when the block size or number of the possible differences in each intermediate state is small, that you can do the matrix multiplication. The third method is introduced by Moriai et al. This method is simple and very fast, but as we will show later, the exact value of the expected differential probability can be very different than the value given by this approach. Moriai et al.'s method is based on the assumption of uniform differential probabilities over one S-box. This assumption says that zero value goes to the zero value by probability 1 and non-zero value goes to a non-zero value by the constant value p, and a non-zero value goes to zero value, and vice versa with probability 0. Note that there is no S-box fulfilling this assumption, but this assumption allows to easily evaluate the expected differential probability of a truncated characteristic. Using this assumption, expected differential probability of a truncated characteristic gets simplified to this equation, that is the multiplication of probabilities for transitioning the activity patterns over the linear layer. For example, in the previous example, in the first round we have 3 active S-boxes that over the first mixed column layer it gets to 1 active nibble. Probability of this transition is that all these 3 active nibbles to be equal. So it is 15 to the minus 2. In the second round, 1 active nibble goes to the 3 active nibbles over the mixed columns with probability 1, and this is the same in the third mixed column. But in the fourth mixed column, we need to fulfill 4 conditions plus the condition that x7 is not equal to the x8. Therefore, using Moriai et al.'s approach for this truncated characteristics, expected differential probability is about 2 to the minus 23.5. As you saw, Moriai et al.'s estimation is only based on the linear layer transitions, and it is independent of the S-box used in the cipher. For the S-box used in the MIDORI block cipher, we used our methods to compute the expected differential probability of this truncated characteristic, and we found that the exact value of this probability is about 2 to the minus 20. As you see, there is a big gap between the value given by the Moriai et al.'s method and the exact value. To show that changes of the S-box can make a significant difference in the value of the expected differential probability, we tried all 4-bit bijective S-boxes and compute the expected differential probability for the same truncated characteristic, and we observed that the minimum probability is about 2 to the minus 22 and the maximum value is 2 to the minus 8. Clearly, the expected differential probability of a truncated characteristic depends not only on the linear layer of the cipher but also on its S-boxes. This was our motivation to present new methods to compute the expected differential probability of differentials and also truncated differentials. In this presentation, I'm going to present the main idea behind our new methods, and for more details, I ask you to see our paper. We start with the definition of expected differential probability of a differential conditioned by a given activity pattern. This probability is equal to multiplication of transitions over each round, and it is summed over all the intermediate values alpha 1 to alpha r minus 1. If we open this sigma and the multiplication, we can bring some of the sigmas inside the multiplication. For instance, you can bring the sigma over alpha 1 until the point that the remaining probabilities are dependent on the value of alpha 1. And for the alpha 2, we can bring it until here, which there is another probability dependent on the value of alpha 2. In this way, you can continue until the point that there is only one remaining sum, which is over the value of alpha r minus 1. This equation offers us a round-by-round method to compute the expected differential probability. In the first step, for each alpha 1 value, we compute the probability of differential transition over the first round and save it in a table T1 indexed by alpha 1 value. Then, in the second round, using the values of table T1, for each alpha 2, we compute this sum, which is over alpha 1, and save these values in the second table T2 that is indexed by the value of alpha 2. In the third step, for each alpha 3, using the values of table T2, for each value of alpha 3, we compute this equation and again save it in another table T3, which is indexed by alpha 3. We continue in this way to reach the expected differential probability of this differential. We denote the set of all possible alpha i's in the pattern with AI. Using this notation, the computation complexity of this method is sum of the computations in each step. And for the memory, in the way that we explained previously, it would be equal to sum over all the size of all AI's. But we only need to keep two consecutive tables. So the memory complexity of our method can be reduced to this equation. We use several techniques to improve the complexity of this method. That, for example, for probability of a truncated characteristic, which is given with this equation, we found out that it is not necessary to consider the first and the last S-box layers. Therefore, this equation gets simplified to this one, which is shortly and more efficient. And this is based on the trivial observation on the bijective S-boxes that for any non-zero value of A, summing over all input differences of X going to A is equal to 1, and the same for summing over all output differences of X coming from A is again 1. Generalizing these equations for a S-box layer, it will be the same condition for the first and the last S-box layer of the truncated characteristic. So it will be again with probability 1, and we can remove it from our equations. Using only the previous technique, removing the first and the last S-box layer, for the previous example of 5-round MIDORI, instead of having sum over 22 variables, now we have only 10 variables, and this reduced the computation from 2 to the 90 to 2 to the 60. Using the state-by-state method, we can bring the alpha 1, which is based on x0 value, until this point, and again alpha 2, which is based on x1 to this point, and alpha 3, which is based on x2, x3, and x4 until here, and the remaining is alpha 4. Then, based on this computation, the time complexity of the state-by-state method will be about 2 to the 44 computations using 2 to the 20 memory blocks. Note that in the previous methods, we didn't use significant memories. So it is somehow trade-off between using memory and time. One can go further and makes this computation more efficient. I mean, instead of computing transition of whole state over one round, we can separate each round to several small steps that to consider only transition over one S-box. For example, this, instead of summing over all three variables of x2, x3, x4, we can separate this over x2 once, and then over x3, and then over x4. And this is the idea for our word-by-word method. Here, I only explain the word-by-word method for the given example, where we separate the sigma over three variables of x2, x3, x4, and this can be like this, where we, for each x1, we compute this parenthesis, and then for each x2, x3, x4, we compute this parenthesis, and then go further and do sum over x2, over x3, x4, and so on. In this way, the time complexity of the method is about 2 to the 21 using 2 to the 17 blocks of memory. But one can also change the order of variables for these sums. Instead of doing sum over x0, one can start with x1 and exchange the position of these sigma. With an optimum order for this equation, it is possible to compute the equation using 2 to the 17 computations and 2 to the 13 blocks of memory. Even so, the example brought here is based on the linear layer using binary multiplication of the words. Our methods can be applied to the block ciphers with different linear layers, and we showed it in our case of studies. We improved our word-by-word method to the block ciphers using creation of the words like a yes or MIDORI here, and present two different advanced word-by-word methods which efficiently can compute the expected differential probability of differentials or truncated differential characteristics. We applied our methods for computing expected differential probability in several block ciphers. We first target MIDORI, Skinny, and Kraft block ciphers, which are very similar. We start with computing expected differential probability of truncated characteristics with the activity patterns with minimum or close to minimum number of active S-boxes. For these characteristics, we found an interesting result that is useful around truncated characteristic for MIDORI block cipher, which Moriai et al.'s method says there is no such a useful truncated characteristic for 7 rounds. Then again, we repeat computing truncated characteristics with activity patterns with minimum conditions in the linear layer. In other meaning, the activity patterns suggested by Moriai et al.'s method. Then in the third step, we compute the differentials within these activity patterns, and we found 8 round differentials for MIDORI, 9 round for skinny, and 14 round for craft. And in the case of linear hulls, we found 6 round for MIDORI, 8 round for skinny, and 13 round for craft. Comparing to previous results, we found 9 round differential for skinny block cipher, which previously was only 8 round, and we improved some of the probabilities for the same number of rounds in the other cases. We also compute the expected differential probability of 4 truncated characteristics of Klein block cipher, which was introduced by Leilmon and Placencia. Computing exact value of these truncated characteristics previously was only based on the linear layer transitions. We used our methods to compute the exact value of these probabilities, and we showed that the estimation by Leilmon and Placencia is very close to the exact values. We also find new truncated characteristics for Prince block cipher, which is comparable to the truncated characteristics introduced by Kanto et al. In this case, we found several new differentials with higher probability. For more details about our results, I ask you to visit our paper. Coming to the end, we present new methods for computing expected differential probability of differentials and also truncated differentials. These methods are extendable to computing expected linear potential of linear hulls. We also present advanced methods for computing these probabilities or potentials for block ciphers with wordwise linear layer. We showed that Moriai et al.'s method even so is very fast and very efficient. The given value with this method can be very different than from the correct value. We also showed that for the same number of rounds, having fewer number of active S boxes doesn't promise better expected differential probability or expected linear potential. Thank you for watching this video, and I would like to hear your comments and questions.